Hey there, ready for another deep dive? Today, we're taking a close look at the work of Dr. James Peebles, this incredible cosmologist who actually won the Nobel Prize back in 2019.
Yeah, he's a pretty big deal.
He's kind of a legend, right? And for good reason. He spent his whole career trying to figure out what the universe is made of, like literally.
Yeah, he's tackled some of the biggest mysteries out there.
Especially, the stuff we can't even see.
A dark side of the cosmos.
Exactly. Dark matter and dark energy. And get this stuff makes up a huge chunk of the universe. Like, think 95%.
It's mind-blowing, right? The vast majority of the universe is invisible to us.
It really makes you wonder, like, what else is out there? But don't worry, today we're going to unpack how scientists figured out these invisible forces even exist.
It's a pretty wild detective story.
And we'll also get a glimpse into the mind of the scientific trailblazer, Dr. Peebles himself.
He's got some fascinating insights into how science works and how we make these groundbreaking discoveries.
Oh, and I almost forgot. We'll uncover this really cool story about a dirty little secret at Bell Labs. It actually led to a major cosmological discovery.
That story is major breakthroughs in the most unexpected ways.
Okay, so before we get to that dirty little secret, let's rewind a bit. Let's trace Peebles' path to becoming this, cosmology superstar.
Because it's not your typical, straight-A physics prodigy story.
Not at all. Peebles actually started out with this passion for building things. He was a tinkerer at heart.
Yeah, he talks about how he loved to take apart electronics and put them back together.
So that led him to study engineering. It makes sense, right?
It does. But as it turns out, engineering wasn't quite the right fit for him.
He realized his true calling was physics.
And thankfully, he had this professor who recognized his potential and steered him towards Princeton.
Ah, Princeton, the mecca of physics research.
Exactly. It was a turning point in his journey.
And at Princeton, he ended up studying under not one, but two giants in the field.
Oh yeah, John Wheeler and Bob Dicke, two legendary figures in physics.
I mean, talk about an incredible opportunity. They both had such different approaches to gravity, and that really shaped people's thinking.
It's like you got the best of both worlds.
So tell me more about these two titans of physics, Wheeler and Dicke. How did their contrasting styles influence Peebles?
Well, Wheeler, he was all about the beauty and the elegance of Einstein's theory of general relativity. He was captivated by, the theoretical side of things.
Okay, so he was drawn to the big ideas, the grand concepts.
Yeah, and Dicke, on the other hand, he was a staunch experimentalist. He believed that theories were only as good as the experiments that could test them.
Yeah.
You know.
So he was all about putting those big ideas to the test, seeing if they held up in the real world.
Precisely. And this emphasis on experimental verification is key to understanding the story of cosmic background radiation.
This is where that dirty little secret comes in, right?
You got it. So we have these two scientists at Bell Labs, Arno Pentheus and Robert Wilson, and they're working with this giant microwave receiver.
This is back in the 1960s, right?
Yep. And they kept picking up this annoying noise they couldn't get rid of, no matter what they tried. They even cleaned out pigeon droppings, thinking that was the culprit.
Wait, so they're trying to eliminate this noise, and it turns out to be, a signal from the Big Bang.
I know, right? It's pretty incredible.
That's wild. But hold on, how did they even know what they were looking at?
Well, this is where Dicke's team at Princeton comes in. They were actively searching for this radiation. They had a theoretical framework to make sense of it. So when word got around about this persistent noise, the two teams met.
And that's when they realized the noise was actually the cosmic background radiation.
The afterglow of the Big Bang. It was a monumental discovery. It confirmed that the universe had a hot, dense beginning.
So two teams, one amazing discovery. What happened next?
They decided to publish their findings separately. One paper detailing the experimental discovery, and the other focusing on the theoretical implications. It was a really great example of scientific collaboration.
It makes sense. But what about the Nobel Prize? I know Penzias and Wilson won it for this discovery. What about Dicke?
Well, that's where things get a little controversial.
Oh.
Yeah, because some people believe that Dicke should have shared the Nobel Prize since his team was, actively looking for this radiation. It raises questions about how we attribute credit in science, especially when discoveries involve a mix of chance and theoretical predictions and experimental confirmation.
It's a good point. And it really reminds us that science is rarely a solo endeavor. It's a collective effort.
Absolutely. And to add another layer to this whole story, the cosmic background radiation was actually predicted even earlier, although less prominently, by George Gamow and his collaborators.
So it's like this chain of discoveries, each one building on the previous one.
Exactly. Science is full of these winding paths and interconnected breakthroughs.
Okay, so we've got this evidence of a hot early universe thanks to the cosmic background radiation. But this is where we start to see the cracks in our understanding of what the universe is actually made of, right?
You're right. There was this puzzle. If the universe started out so hot and dense, how did it end up with the clumpy distribution of galaxies we see today? The cosmic background radiation suggested a smooth, uniform beginning, but the universe we observe is anything but smooth.
So how did Peebles tackle this cosmic conundrum? This is where dark matter enters the picture.
Exactly. Peebles had the audacity to propose something radical. What if there was an invisible substance out there, something that didn't interact with light but still had mass and gravity? He called it dark matter.
So Peebles just throws out this idea of dark matter, like out of nowhere. Was there anything that led him to this radical idea?
Well, it wasn't completely a guess. Astronomers had already noticed something strange, like galaxies were rotating way faster than they should based on what we could see, the visible matter.
That's like something was missing.
Yeah, exactly. Like some invisible glue was holding these galaxies together, providing extra gravity.
So dark matter was like the missing piece of the puzzle. It explains why galaxies behave the way they do. But how do we actually know this isn't just like a made-up concept? How do we know dark matter is real?
Okay, so Peebles didn't just propose the idea of dark matter. He went a step further and suggested that it was cold, meaning it moves slowly, compared to the speed of light.
Cold dark matter. Okay.
And this was a crucial insight because it led to some very specific predictions about how dark matter would clump together over time.
So this cold dark matter would have shaped the large-scale structure of the universe, like the way galaxies are distributed. But how do we test that idea? I mean, we can't see dark matter, right?
Right. But remember that cosmic background radiation we talked about?
Yeah.
The afterglow of the Big Bang? Well, it turns out those tiny temperature variations in the cosmic background radiation, the wiggles, are like fingerprints.
Fingerprints of matter.
Yeah, exactly. They reveal the presence and properties of dark matter.
Okay, hold on. I need a bit more explanation on those wiggles. Can you break it down for me?
Sure. So imagine you're taking a snapshot of the baby universe. This snapshot would show tiny differences in temperature, like hot spots and cold spots. These wiggles are essentially a map of those temperature differences.
Okay, it's starting to get it.
And the pattern of those wiggles tells us a lot about what the universe is made of, including dark matter.
So Peebles' theory of cold dark matter actually predicted these wiggles.
Exactly. And here's the amazing thing. When astronomers measured the cosmic background radiation with super high precision, the pattern of the wiggles matched Peebles' predictions almost perfectly.
Wow, so it was like a confirmation of his theory.
Exactly. Strong evidence for the existence of dark matter.
That's really cool. It's amazing how these theoretical predictions can be tested by looking at this faint light from the Big Bang.
It is pretty mind-blowing.
So we've got dark matter, this invisible glue, holding galaxies together and shaping the universe. But the story doesn't end there, does it? There's more to the dark universe.
Oh yeah, there's more. The plot thickens, you could say.
Mm.
Because the universe isn't just expanding, it's expanding at an accelerating rate. And this is where Einstein's cosmological constant comes back into play.
Wait, the cosmological constant, the thing he called his biggest blunder.
The one and only.
Okay, so back up a sec. What is this cosmological constant, and why did Einstein think it was such a blunder?
Okay, so Einstein added this constant to his equations of general relativity because he believed the universe was static, like neither expanding nor contracting, So this constant was a way to counteract gravity and keep the universe in balance. But then Edwin Hubble discovered that the universe was actually expanding, and Einstein was like, oops, my bad. He abandoned the cosmological constant, calling it his biggest mistake.
So why are we even talking about it now? What does this have to do with dark energy?
Okay, so in the 1990s, astronomers were looking at distant supernovae. These are exploding stars, right?
Right.
And they realized these supernovae were dimmer than expected, suggesting they were farther away than they should be.
That's interesting.
Yeah, and the only way to explain this was if the expansion of the universe was speeding up, not slowing down like gravity would suggest.
So the universe is not only getting bigger, but it's doing so at a faster and faster rate.
Exactly, it's accelerating. And to explain this accelerating expansion, scientists needed something new, something, more than just dark matter.
Enter dark energy.
Right. So they resurrected Einstein's cosmological constant, this idea he discarded, and linked it to this mysterious force, this dark energy that seems to be pushing everything apart.
So Einstein was right all along. This biggest blunder of his might actually be a crucial part of understanding the universe. That's pretty wild.
It just goes to show you that science is constantly evolving and that sometimes old ideas can come back in a big way.
And Peebles, he played a role in this whole dark energy saga, didn't he?
Oh, absolutely. He was one of the first cosmologists to really seriously consider the cosmological constant again as a way to explain this accelerating expansion. He even joked about, a younger scientist accusing him of bringing it back just to annoy people.
He seems like he has a good sense of humor about all of this.
Definitely. But beyond the jokes, his willingness to revisit old ideas, to consider these unconventional solutions, it was critical to moving the field forward.
That's amazing. So we've gone from a universe we thought was mostly made up of stars and galaxies to one dominated by these invisible forces.
Dark matter holding things together and dark energy pushing them apart.
It really changes our whole perspective on the cosmos.
It does. And it raises a ton of new questions, like what are dark matter and dark energy really? How will this accelerating expansion affect the fate of the universe? The big picture stuff.
It's mind-boggling. But before we get too lost in the vastness of it all, let's zoom in a bit. Let's talk about this specific galaxy that Peebles talks about, M101.
Ah, yes, M101. It's a beautiful spiral galaxy.
And Peebles sees it as like a microcosm of all these cosmic puzzles we've been talking about. So what makes this particular galaxy so special? Why M101?
Well, first off, it's just a really beautiful galaxy visually. I mean, with these bright blue star-forming regions and red patches of ionized plasma and the central yellow glow, it's just a stunning reminder of just the beauty and the complexity of the universe.
It sounds gorgeous. I mean, just like this cosmic masterpiece, but you're saying there's more to it than just how it looks, right?
Right. Peebles points out that M101, it probably has billions of planets,
Wow.
most of which we'll never even be able to observe directly. It's
Yeah.
just this thought that's so humbling that there's so much out there beyond our reach.
It really is. But even with the parts of M101 we can observe, there's still so many like puzzles, right?
Oh, yeah, absolutely.
Mhm.
One of the big mysteries is its thin disk and these really tightly wound spiral arms. Even with everything we know about dark matter, our current simulations, they still can't really reproduce those features.
So it's like something's still missing from our models of how galaxies actually form and evolve.
It seems like it, yeah. Like there might be this key ingredient or some process we just haven't fully accounted for yet. And then there's the question of whether M101 even has a supermassive black hole at its center.
I thought most galaxies had supermassive black holes at their centers.
Yeah, a lot of them do, including our own Milky Way. But for M101, it's still kind of an open question. But the James Webb Space Telescope, with its amazing sensitivity, it might be able to detect the signs of a black hole hiding there.
That would be so cool. Speaking of the James Webb Telescope, it's been making all these groundbreaking discoveries about early galaxies, and some of them seem to, challenge our current understanding of galaxy formation, how quickly they formed. What does Peebles think about these new observations?
Well, he basically sees it as another clue, another piece of the puzzle. He knows these observations. They kind of challenge our models, and it might mean we need to rethink our understanding of galaxy formation. He seems excited to see how the next generation of cosmologists are going to take on these new challenges.
It's amazing how even with everything we've learned, there's still so much we don't know about the universe.
I know, it's really humbling.
Yeah.
And Peebles actually has a great perspective on this. He talks about how important it is to go back and look at these little oddities, these weird observations that might have been ignored or overlooked.
Like those pigeon droppings.
Exactly. Sometimes the biggest breakthroughs come from paying attention to those little details that don't quite fit.
It seems like he's really comfortable with not having all the answers.
He is. He thinks that some questions like the ultimate origin of the universe might be just beyond our reach for now. And he doesn't see that as a failure of science, but just the acknowledgement of how vast and complex the universe really is.
That's a really cool way to think about it. And it makes me think about all those billions of planets in M101 that we might never be able to see. What if we could see them? What would we find?
I know, right? It's a question that really sparks the imagination.
Yeah.
Would we find life, maybe even intelligent life? Would those planets be like ours, or would they be completely different, shaped by forces we can't even imagine?
It's incredible to think about all the possibilities out there. This deep dive into Peebles' work has been amazing. It's really opened my eyes to all these mysteries, the invisible forces that shape the universe, and those big questions about its origin and its fate. It's been a wild ride.
Yeah, it has. And it's a journey that never really ends. The more we explore, the more we observe, the more we'll uncover new and amazing things about the cosmos.
So to everyone listening, keep looking up at the night sky with that sense of wonder. Keep asking those big questions and keep exploring. You never know what you might discover.